I believe this is possible thanks to a huge breakthrough that solved one of the biggest mysteries in science: figuring out the structure of proteins. To understand how big this is, imagine thousands of scientists working for over 60 years to figure out the shape of just 150,000 proteins. Then, in just a few years, a small team of only 15 people managed to solve the structure of 200 million proteins. That's basically every protein in nature. So, how did they do it? And why is this such a big deal? Proteins start as long chains of tiny building blocks called amino acids. Each amino acid has three main parts: an amine group on one side, a carboxyl group on the other, a side chain that makes it unique. There are 20 different ones. These amino acids connect like links in a chain, forming a long strand. But this strand doesn't stay straight. It twists, bends, and folds into a 3D shape, influenced by forces like electrostatic charges, hydrogen bonds, and surrounding molecules. And this shape is everything. The function of a protein depends on its structure. For example, hemoglobin has a specific shape that allows it to carry oxygen in our blood. Muscle proteins change shape to help us move. If a protein folds incorrectly, it won't work properly. For decades, figuring out these shapes was extremely slow and difficult. The first way scientists did this was through a method called X-ray crystallography. They would turn a protein into a crystal, shine X-rays on it, and study the pattern that formed. Then they had to work backward to figure out the protein's actual shape. This process was incredibly slow. A scientist named John Kendrew spent 12 years just figuring out the shape of one protein called myoglobin, which helps store oxygen in muscles. At first he tried using a horse heart, but the crystals were too small. So he got a big chunk of whale meat from Peru, which finally gave him the results he needed. But when he saw the final structure, it looked nothing like what scientists expected. Instead of something neat and symmetrical, it looked like a messy, tangled knot, almost like the inside of a complicated machine. Some scientists even joked and called it the turd of the century. Still, this discovery was so important that Kendrew won the 1962 Nobel Prize in Chemistry. Even after this breakthrough, progress was very slow. Over the next 20 years, scientists managed to figure out only about 100 more protein structures. Even today, crystallizing proteins is one of the hardest things to do in biology. For some researchers, solving just one protein structure can take years. Sometimes their entire PhD is focused on just one. The process is also super expensive, costing tens of thousands of dollars per experiment. And yet, despite all these challenges, a tiny team of 15 researchers recently did in a few years what thousands of scientists couldn't do in 6 decades. How? That's where the real revolution begins. Why are proteins so complicated? Figuring out a protein's structure has always been a huge challenge. The traditional method, X-ray crystallography, was slow, expensive, and difficult, costing tens of thousands of dollars per protein. So, scientists started looking for a better, faster way. It turns out finding the sequence of a protein, the order of its amino acids, is much cheaper, only about $100. If scientists could use this sequence to predict how a protein folds, it would save a lot of time, effort, and money. At first, it seemed possible. We know how atoms like carbon, sulfur, and nitrogen behave. We know how certain chemical bonds form, so in theory, if you understand basic molecular forces, you should be able to predict how a protein will fold. In fact, one of the few correct predictions in biology came from Linus Pauling, who studied the shapes of protein building blocks and predicted they should form helices, spirals, and sheets. This became known as secondary structure, the first level of protein folding. But beyond these simple shapes, things got way more complicated. Scientists realized that proteins don't follow neat patterns. One big reason? Evolution didn't design proteins from scratch like an engineer would build a machine. Instead, evolution kept modifying and adding onto existing structures whenever something worked. It's like a messy programmer who doesn't plan ahead, but just keeps adding things until the program works. The result? Proteins are both incredibly amazing and ridiculously complex. To show just how complex, MIT biologist Cyrus Leventhal did a quick calculation. He found that even a tiny protein with just 35 amino acids could fold in an astronomical number of ways. How big is this number? Imagine a supercomputer checking 30,000 possible protein shapes every nanosecond. Even at that speed, it would take 200 times the age of the universe to find the right structure. This is why predicting protein folding was considered impossible for a long time, until a major breakthrough changed everything: the Casp competition and DeepMind. Even though predicting protein structures seemed nearly impossible, a scientist named John Molt from the University of Maryland refused to give up. In 1994, he started a competition called CASP, Critical Assessment of Structure Prediction. The challenge? Scientists had to create computer models that could take an amino acid sequence and predict how it would fold into a protein. The twist? They wouldn't know the correct answer in advance. Their results would be compared to real protein structures determined through experiments. The scoring system worked like this. A perfect match scored 100. Anything above 90 was considered a solved structure. Early attempts scored below 40, not great. Every few years, Casp competitors gathered in Monterey, California, at a small, old chapel-turned conference center. If someone's predictions didn't make sense, others would tap their feet as a playful way of teasing them. There was a lot of foot-tapping in the early years. One of the early leaders in protein prediction was Rosetta, a program created by David Baker from the University of Washington. To speed up calculations, Baker used a clever trick. He borrowed computing power from people's home computers, schools, and libraries through a project called Rosetta at Home. But something surprising happened. The project had a screensaver that showed how the program tried to fold proteins. People started watching it closely, and some believed they could do better than the computer. So Baker had an idea. He turned protein folding into a video game. The game, called Fold It, let players manually twist and fold protein chains into different shapes. Instead of the computer guessing the best fold, humans could try, and it worked. Within just 3 weeks, over 50,000 gamers helped solve the structure of an important HIV-related enzyme. Scientists confirmed their solution was correct using X-ray crystallography, and the gamers were credited as co-authors on the research paper. One of these Fold It players was Demis Hassabis, a former chess prodigy who later founded an AI company called DeepMind. His AI, AlphaGo, made headlines when it beat the world champion Lee Sedol in the board game Go. One move, called Move 37, was so shocking that Sedol was visibly shaken. But Hassabis never forgot about Fold It. He wondered, could AI mimic the intuition of those gamers and predict protein structures? So, after returning from Korea, Hassabis and his team held a week-long hackathon at DeepMind. Their goal? Train AI to play Fold It. This led to a bigger idea. What if AI could solve the protein folding problem completely? DeepMind launched AlphaFold, a new AI project focused on predicting protein structures. At the same time, progress at Casp competitions had slowed down. Even Rosetta and other top models weren't improving much. Faster computers and more protein data weren't enough. DeepMind wanted AlphaFold to change that. Their first version, AlphaFold 1, used a standard deep neural network, similar to the ones used in computer vision. The researchers trained it on thousands of known protein structures, hoping it could learn to predict new ones. This was just the beginning of a breakthrough that would change biology forever. How does AlphaFold work? To predict how proteins fold, AlphaFold uses clues from evolution. Proteins evolve over time due to mutations, small changes in their amino acid sequences. But proteins still need to keep their shape to function properly. That's why hemoglobin looks the same in humans, cats, horses, and most mammals. Evolution follows the rule. If it ain't broke, don't fix it. Scientists can compare protein sequences from different species in an evolutionary table. If many species have the same sequence, that part of the protein is probably important. If mutations happen in pairs, it can reveal which amino acids are close together in the final folded structure. For example, suppose lysine, positive charge, and glutamic acid, negative charge, are next to each other. attracting each other and stabilizing the protein. If lysine mutates into a negatively charged amino acid, it would repel glutamic acid, destabilizing the protein. To fix this, another mutation must change glutamic acid into a positive amino acid. This is called coevolution, and it helped AlphaFold make better predictions. How AlphaFold uses this data. Instead of directly predicting a 3D protein structure, AlphaFold first creates a simpler 2D map. The amino acid sequence is placed along both the horizontal and vertical axes. Whenever two amino acids are close together in the final folded protein, their intersection lights up on the map. Distant amino acids appear dimmer. This map also stores information about how the amino acids twist in the final structure. AlphaFold's first big test. In Casp13, AlphaFold entered the competition and immediately stood out. It won first place, but it wasn't perfect. It scored 70, which was not enough to reach the Casp threshold of 90. To improve, DeepMind brought in John Jumper to lead AlphaFold 2. How AlphaFold 2 got better. Instead of adding extra steps, AlphaFold 2 was designed from the inside out to focus on learning about proteins more effectively, using geometric, physical, and evolutionary knowledge inside the deep learning system. This massively improved accuracy, bringing AlphaFold even closer to solving the protein folding problem. AlphaFold 2's big victory. In December 2020, DeepMind's team returned to the Casp competition with AlphaFold 2, and they stunned the world. Their AI system was so accurate that its predictions almost perfectly matched real protein structures. John Molt, head of Casp, said in an email, "Your team has performed spectacularly in Casp14, both in relative and absolute accuracy." AlphaFold 2 surpassed the 90-plus gold standard accuracy threshold, a historic achievement. AI has propelled science forward. In the past 60 years, scientists discovered only 150,000 protein structures. In just a few months, AlphaFold 2 predicted over 200 million protein structures. This revolutionized biology and medicine, aiding in malaria vaccine development, breaking down antibiotic resistance enzymes, understanding schizophrenia and cancer-related protein mutations, discovering protein structures in rare and endangered species. AlphaFold 2's research paper has been cited over 30,000 times. And in 2024, John Jumper and Demis Hassabis won the Nobel Prize in Chemistry. The future of AI and science AI's impact on medicine and science is just beginning. DeepMind's GenoME program has already discovered 2.2 million new crystals that could be used in superconductors and batteries. One scientist summed it up: if AI were just 2 times faster, it would be helpful. But when AI is 100,000 times faster, it changes the very nature of science. The future promises more breakthroughs, perhaps even cures for every disease, revolutionary new materials, and a cleaner planet. Let's just hope AI doesn't destroy us first.